Yeah.
Exactly.
I wanted to ask Isaac, even care, like what happens before the lights go off? Like from the generation point of view, like do they just go off? Do the machines try and do something before we go to a blackout? What exactly happens as that is happening?
Okay, yeah. Now, to the viewers out there, that's a kind of question that shows the engineering mind of the person, that inquisitive nature. Anyway, what happens? So, one, we must state that the power station we're talking about has what we call rotating machines. Unlike solar, just static machines. So the machines are rotating because of water that is heating these machines. So, when a disturbance happens, say I'll give an example, I think from the most recent blackout, I think it was when UTCL communicated on their X. I think this was public. Talked about how they had some disturbance somewhere, and then eventually, unfortunately, we descended into a blackout. So let's say you have two transmission lines that are heavily loaded. So it's like peak time. Peak time, I mean, say somewhere maybe between 7 p.m. to about 9:30 or 10 p.m. Everyone is maybe watching TV, maybe some watching World Cup. Maybe now because of the time zones, it wasn't a thing, but maybe people are streaming, some are doing homework, people, washing machines are on, washing clothes and stuff. So it's like peak time. Many of the things are on, drawing a lot of power. So, if all of a sudden I'll give a scenario. Say you have two transmission lines evacuating one power station. Each line maybe can carry a maximum of, say, 150 megawatts. 150 megawatts, other one is carrying, other one can also carry 150 megawatts. Say they're loaded at about 140. That's about 280 megawatts. And they're evacuating a power station where 4 generators are loaded. Let's say each is 40 megawatts. That's about 160 megawatts. So the power that these generators are producing is being taken away by those two transmission lines. One transmission line maybe gets a problem. Maybe there's a loose jumper, a broken jump on the line. Broken jump on the line causes a fault. Not to go into so much detail of that kind of fault. Maybe it's a single phase to arc fault, phase to phase fault. It's going to trigger, say, the main protection on that line, and that line will trip. Let's say the line tries to auto reclose. There's something called auto reclosing. It tries again. It tries to close the circuit breaker again to try and see and check if the fault is still there. If the fault, say, was temporary, maybe a bird flew by or wind blew and wires touched and they released, it will close and everything will be safe. But if it tries to close again and finds the fault is permanent, it will now, what they call lockout. That circuit breaker will not be able to close anymore, or the switch. So anyway, that line goes off. Now because there are only two lines, the other line was on. Let me call them line 1 and line 2. Line 1 that was carrying 140 megawatts suddenly trips. That means the circuit breakers on both its ends, from the power station and the other end where the line is going, say a substation somewhere, both of them open. So the 140 megawatts that line was carrying has to be carried by something else. Because let's say it's supplying a substation or supplying a place where maybe people's things were still connected into the sockets. TVs were on, whatever was on, all that 140 megawatts is. By the people's homes, maybe someone, people are still at work, there's a factory running. So that load is still there. So it's going to be, should I say, transferred to the other line. So that other line now is going to carry 280, because it was carrying 140 before, now it's carrying an extra 140. 280 megawatts. Yet the line has a maximum of 150 megawatts. It's going to get overloaded. It can't carry. Say you're in the gym, your personal record or your best, the most you have lifted, say you're doing a bench press is like 100 kilos. All of a sudden, you decide to carry 250 kilos without any training. Something. You have to lose something. Maybe your shoulders have to go or something like that. So, that's the kind of thing. So that line 2 also now goes off. Now, when that line 2 goes off, that was the load on the generators. If maybe, so now when that load is on those generators are being rotating. So they've been rotating, there's an amount of water that has been pushing them. At that instant, when those two lines go off, And that could happen in like 10 seconds even, or 5 seconds.
Right.
Yeah. That water is still trying to push the generator, but the generator now is not loaded, it's not carrying anything. It is going to speed up, the overspeed that Isaac was talking about earlier. Say it has been rotating at 150 revolutions per minute. Now, because it's not carrying anything, it may speed up to 180 revolutions per minute, may speed up to 190 revolutions per minute. And when that happens, the frequency on the network changes. Remember we said frequency is what characterizes stability. So there's a relation between speed and frequency. I think there's a formula, which is an expression, a mathematical expression. N is equal to 120 times F over P, where N stands for the speed in revolutions per minute, F stands for frequency, and P is the number of poles on the generator. So a generator has a rotor with poles. So speed and frequency are directly proportional. When speed increases, frequency on the network increases. So frequency goes out of that dead band that Nicholas had talked about. 50.5 starts rising up, 51, 51.5, 52. So depending on the rate of change of frequency, it can even reach up to like 55 Hz. Now we have... So anyway, as all that is happening, Nicholas had asked, so what is happening on the side of generation? Now it has gone out of the dead band. The generators have a governor system, a speed control system. It tries to pull the machine back to its normal speed. So it was at 150, it has gone to 180, it's rising. It tries to pull the machine back to its normal speed of 150 by reducing the amount of water that is hitting the machine. So controlling the mechanical input. That means, how does it do that? There's some gates we call wicket gates. It reduces their opening, so less water hits the machine and the machine can slow down. So depending on what is happening on the network, is the frequency going up, is the frequency going down, it can either increase the opening to allow more water or reduce the opening. So the governor system is trying to control the machine, get it back into stability. Stability, I mean the stability of rotation. It's not just going haywire and spinning out once. 1 get 150. So the governor is trying to control that depending on how the frequency is moving. Sometimes the governor system can fail because the grid is big. There are other machines elsewhere that are also supposed to be trying to control their frequency, but sometimes due to one reason or another they can fail, and one power station alone on a big network cannot control the frequency for the whole network. Yeah. All these machines come into play, they hold hands to make sure they control the frequency, and then so if all these governor systems or any other frequency control systems fail on the network, then eventually that's when protection might come in, either to take the machine off on a lower frequency. You can see a cascade of trips. Now those machines that were being evacuated by line 1 and 2, all of a sudden they speed up and they can trip off the grid on over frequency. Yeah. Now that could happen, it could, now the frequency might come down, going to under frequency. Then depending on how long it stays there, because it's under frequency, some machines start to get overloaded as well. You may see things like overcurrent protection starting because they're starting to produce more current. Because now you have less generators, but you still have a very big load. Yeah. Say you have 20 generators, and say you have 20 loads. Let's say 20 factories connected. If out of those 20 generators, 12 of them switch off for one unknown reason, at one instant you're going to have 8 generators still trying to serve 20. So now the generators start to get overloaded. They're trying to produce so much current for all of these. That's why the overcurrent would come in. So you start to overload the generators. So sometimes, not sometimes, on some transmission lines, transmission has what you call a load shedding scheme. So instead of all these 8 generators trying to feed that 20, should I say, factories connected, that load shedding can start to cut off some factories. It's able to do that automatically through the protection relays, and maybe cut off like some 10 factories that go. So that you can maintain the stability of the frequency. Then when things are back to normal, you can start to connect the other. So it's like a dance of sorts. Yeah, like frequency going up, down, and all these machines are connected. Machines I mean the generators in Kenya, in Tanzania, in Rwanda, all the places are connected to. All of them are trying to should I say, come together to try and control the frequency through the different frequency control mechanisms. Governor systems, they have there's some places where you have base systems, that's battery energy storage. You can have what we call the power system stabilizing excitation systems. You have that. Those are also, you can be able to manage your stability with those different systems. So like Nicholas had said, for you in your house, it may seem like power has gone off at the same time because everyone lights will go off at the same time. But from the side of the power station, the generators have tried, they've taken their time. They don't just switch off immediately. They try and make the frequency a straight line. So if it's like a graph, say on your y-axis you'll have frequency. The units of frequency are Hz, Hz, capital H, small z. Don't forget the capital H. Don't just write small h, small z. That's unacceptable. And then on the
HAS.
Yeah, or HAS, no. It is HERTZ. So on your x-axis you have time. Say maybe minutes, hours, whatever. So you have like almost like a straight line of frequency from like 50. So you draw like a line from 50, maybe like a wave. So, but not exceeding, say 50.5, not 49.5. But as it starts to spike up, down, that causes the generators to start to respond. And what they're trying to do is bring that frequency back to a straight line and remove spikes and remove dips. So they try for some time, however, sometimes the situation network is not very good. And then they will not be able to do their job, and then power will then start to cascade into.
I wanted to ask Isaac, so do you be chilling as the machines are trying to control the grid? What as an engineer, what do you be doing to save the situation?
Man, at that point in time, honestly, it is a machine is our time to of course, before you take any action, you need to know why it's behaving. You're trying to figure out why it's behaving the way it is for the most part. So, of course, the machine, of course, it's audible. You try to know that something's wrong with the machine if you're inside. So, in that instant, as the machine is trying to regulate the load, trying to balance out things, at that point in time, you may not exactly know what is causing it to behave that way. So, you're trying to investigate, trying to find out, of course, taking out different parameters, you're observing what's happening. Is the frequency okay? Do we have all the feeders still in? Other machines which are tripping. So you're trying to understand, get a full picture of what's going on before you can take any action. And for the most part, all this happens really quickly before you can really do much, about anything. So honestly, you for the most part, you're just watching what's happening just to understand everything, because you can't just start touching things before understanding the picture of everything. I think that's it. But no, it's like it's like it reminds me of a question someone asked me. When power goes, some people live like a light to certain power comes, like I know that power is back. So sometimes maybe you leave your TVs or whatever appliances which you're watching on. Is that dangerous? Because they're asking me, is it bad? Honestly, I've never seen a bulb blow because it was left on when power was gone. But as kids growing up, we're told, man, switch off all the lights, switch off everything, plug out the cable sockets. So is it dangerous for us to leave our things plugged in during this? Because we didn't know that power has come back.
Well, first, before maybe answer that, just like what Isaac was saying, these things are happening very fast. That's why we live many times. Okay, the human may not have much to do at that time, so you hand the job over to those automatic systems that are quickly able to respond. Because sometimes you may find, like I think in the last incident, that was on 5th June, the frequency was changing at a rate of 1.8 Hz every second. So as a person here, they don't really. So by the time it can move from 51 to 55 in about 2.9 seconds. How long does it take to for the light to blink? Okay, yeah. I'm just trying to say 2.8
A second,
seconds. Yeah,
yeah.
yeah. You may not have enough time to do much as an operator, so the automatic system is coming. Now, for what Isaac was asking, now I think our parents were engineers, but they didn't know it. Because there was some truth to it. Because sometimes, like actually in the last incident, one thing that was noticed was at some point there were very high voltages on a bus bar that should have 132 kilovolts. At some point, in some places, at about 145 kilovolts. So sometimes, because of the things that are happening on the network at that time, if maybe they try and restore, and maybe the voltage is very high, depending on how also on the voltage the final gets to your house. If it also happens to be high, so some equipment is more sensitive than others, especially electronic equipment. So that's why you find maybe they may tell you connect your TV to the wall through a guard or something like that, something that can regulate the voltage, give your TV good voltage or good pressure, like we talked about in the first thing. So sometimes you may find that might happen. It rarely happens, but it could happen, and something can blow. Yeah, that could be the danger. So I think our parents were right. Maybe try and switch off as many things as you can. Maybe leave one bulb on, a sacrificial lamb of sorts. Yeah, something. Of course, if it's, but yeah, something. Like, if you really want to do that, leave like a bulb on, something that's not too expensive. Not a fridge, not a TV. So yeah, something else. But that rarely happens. I think many of us are not going to say. Are going to say we haven't seen that happen, but it could. It can happen.